Good morning from Detroit. My name is Wei-Song Shi, the Associate Dean for Research and Graduate Studies at Wayne State College of Engineering. Today is the fourth Jessup seminar series, and we are very happy to have Dr. Caisheng Wang from ECE department that will give us a talk related to the smart grid, electrical, power electronics, and etc. So before that, let me invite Dean Farshad Futui from engineering to give a welcome remarks. Farshad?
Thank you, Wei-Song. Thank you. And I'm very excited to be here with you guys this morning, and also being able to listen to the Professor Caisheng Wang's work that he's doing with his students in our lab. As Dr. Wei-Song Shi, who is our Associate Dean for Research in the College of Engineering, mentioned, that we have started these seminar series going all the way up to August, every Friday from 9 to 11 Eastern Standard Time, that we wanted to really reach out to our alumni globally. We want to reach out to our industry partners globally, as well as, more importantly, reaching out to our university partners globally. And that way, their students, their faculty, get better understanding of our work that we are doing in our college, with our faculty in various research areas, because most of our collaboration with our partner universities have to deal with exchanging students, or students from there to come here and study. But we always had an eye toward building research collaborations with our partner universities, their faculty and their students. And we believe this seminar series will help us to really introduce some of these faculty to your students. So if they decided to pursue advanced degrees, then they know who are the faculty, the kind of work that they are doing, and hopefully they can then consider Wayne State as a destination for their advanced programs here. Or if they want to visit, or if you are one of your faculty member wants to spend sabbatical with us, you're more than welcome to join us for a sabbatical. Again, some of the work that some of the faculty are doing in that regards. We were hoping that starting in the fall, September, going forward, we will have these continued. The college has about 130 faculty members. We have many also visiting faculty, part-time faculty, lecturers, and so on, that are engaged in research and teaching. We have about 3,500 students. 300 of them are PhD students, and about 600 master's students, and the rest are undergraduate students in 8 departments. Computer science, which Professor Wei-Song Shi belongs to. Computer science is part of the college. Electrical and computer engineering, Dr. Caisheng Wang. We have biomedical engineering that you're going to be hearing from one of the faculty there later in the seminar series. We have Department of Civil and Environmental Engineering. We heard from Dr. Steve Ramius last week about a smart infrastructure and smart cities. We have Department of Chemical Engineering. We're going to hear from Dr. Helen Duran later on in month of August, I believe, during the seminar series. And we have engineering technology. A couple of our faculty in engineering technology currently are teaching a course for a partner university in China. And again, they're not part of the series, but they're engaged in teaching to our partner universities in that case. And we have Department of Industrial and Systems Engineering. Again, we will have a presentation from a faculty member from that department later on. And I think that listed all of them. If I missed somebody, you can correct me on that. With that, I encourage you to join us next week also. And also in the fall, we will hopefully continue our Coffee with the Dean seminar series. Again, those are usually we bring in a panel of experts, including our faculty, to talk about some topics which are maybe focused around sustainable development goal. One last thing that I want to mention is that these seminar series are under the umbrella of Nancy Philippard and McGrail Global Engineering Education Center that we have established in the College of Engineering. with the gift from Dr. Nancy Philippard and her husband, gift of $1 million to establish this global engineering education, to really make sure that our engineering students at the College of Engineering are not only focusing on the work that is done in Detroit and surrounding areas, but globally being able to think and being able to collaborate and be successful. So we want to get every student get a global experience, either by traveling or participating in collaborative teaching that we are doing right now currently with some other universities. So we have done many areas in which we wanted to get our students their hand involved in those. With that long welcome, again, thank you for joining us today. And I look forward to seeing some of you hopefully in the next week seminar series. Wissam?
All right. Thank you, Farshad. I guess the people are eager to listen to hear Dr. Wang's talk, but I still want to give a very brief introduction about him. That Dr. Wang actually has been in this area for more than 20 years. Is a world well-known expert on the power system, starting with the smart grid and then on the electrical vehicle and power electronics. This is a particularly hot topic today. As the world is moving from the traditional gasoline-based powered vehicle to the electrical vehicle and etc. So he has been published tons of papers in these areas and also writing several books in this area. So without further ado, I will give the podium to Dr. Wang. Go ahead.
Thank you very much, Wissam, and also Dean Fatui for your kind introduction. So Kristen, can I share my screen now?
You should be good to go.
Good.
Okay. Give me a second. All right, I hope you can see my screen now.
Yes.
Yes.
Wonderful, thank you. Yeah, so once again, Wissam and Dean Fatui, thank you very much for your introduction there. And thank you all for coming to today's seminar, which is a part of a series, seminar here. So my talk today is on a hybrid and a diversified approach to sustainable, reliable, resilient, and affordable electric energy development and delivery. I believe Dean Fatui has given a very informative introduction about the college. I just want to share some facts and numbers about the college. So I believe 3 years ago, the university celebrated its 150 years anniversary, and the whole university have like 274,000 alumni worldwide, and for engineering we have 30,500 alumni. So currently we have 300, almost 400 students here. So about 76% of them are bachelors, and about 25% of them are graduate students here. So among like the major research universities in Michigan, we have like University of Michigan, Michigan State, and Wayne State. Wayne State, we have the lowest tuition, so it's very like cost effective. And we are located in the midtown of Detroit. And Detroit is the capital of auto industry, particularly now we're talking about electric vehicles. And the engineering College of Engineering has more than 130 full-time faculty members. And Dean Fatui also gave the introduction there about the various departments in the college. So we have seven departments and one divisions, engineering technology divisions, and many of them are ranked top 100 for the graduate programs, according to the U.S. News here. And yeah, well, for the EC department, we was ranked maybe 70, 80 there, but just, sometimes up and down there, and just kind of, now it's kind of drop a little bit out of that 100 there. So I want to take this chance to give a quick introduction about the EC department. The department was established in 1933. It's 88 years ago. And I think, the department was one of, the first initial departments, like when the college was established. Right now we have 24 full-time faculty members, and doing research and teaching in integrated circuit design, micro and nano devices, robotics and embedded systems, signal and information processing and control, power and energy, and also intelligence, like machine learning, in those various areas. And I did a little bit like the research on the history of the EC department. Actually, we have glorious history. Now, if you look at, I'm not sure whether you can see it here. It's a little bit small here, the font. But, the EC alumni are a group of proud people with, very famous professors in top universities and research institutes like the University of Michigan, Cornell, Carnegie Mellon, UIUC, etc. And also members of National Academy of Engineering. And successful industry and business leaders. So I certainly, I'm pretty sure, in the future we can add, more names there from our the future like alumni there. So a little bit more like the facts and numbers about our EC department. We as you see from the figure here, the undergraduate enrollment actually is growing steadily. In the past couple of years, although we see some decline in graduate enrollment there, but that's like not a particular department issue, or not just a particular college issue, like the university wise, and also probably the national wise. We see that kind of trend, but it's really I'm glad to see that the undergraduate enrollment is really strong and steadily growing here. So we have a Bachelor of Science in the Electrical Engineering, but the department now is talking about to change the name to ECE to actually match the department name there. We have master's degrees and also the Doctor of Philosophy in computer engineering and also in electrical engineering. So, as I said in the previous slides here, so the faculty are doing active research in various areas here in the ECE, like control, micro and nano sensor devices, integrated circuits, power systems here, robotics, and so on and so forth. And as you can see here, those are the books published by the ECE faculty members. I may miss some of them, but this is the one I got by that time. So with that, let's get started today's the seminar. I like this slide. I've been using this slide quite a bit. A couple of years ago, National Academy of Engineering actually did a survey about the greatest engineering achievements in the past century, in the 20th century. So I asked the audience, so what kind of the great achievements of engineering you can think of? So as you see here, 20 greatest engineering achievements are listed here, but the number one here is electrification. So with the electricity, we make a lot of things happen. We enable a lot of things. So this is really a fundamental thing. It's like it's a necessity to many other modern technologies there. So in today's talk, I'll start with like a quick like a review of different systems in the power system there, like from the generation to transmission and to distribution. So normally we're going to generate electricity from various sources, but when we want to deliver the electricity over long distance there, we need to boost the voltage up and transmit it over the transmission network there, and then go to the distribution system to deliver the electricity to end users. So today I'm going to review those things with you, and we'll talk about the challenges we're facing now in today's like power systems, and then talk about the possible solutions to address those challenges, and also we're going to talk about what our work and our approach and activities in part of that effort. So now a little background about power system here. So this is like utilities in the past. So we have, in the past, we have a vertical structure. It's a utility company may own generation facilities, as well as transmission asset, as well as a distribution network here. So a utility company can own all of them. So and then back in 1992, people realized that may not be good for competition. So in 1992, the Energy Policy Act was passed. Then in 1996, the FERC issued the order 888 to basically like for the deregulation of the utility. So in particularly in 1999, the FERC issued an order 2000 for establishing those what we call the independent system operator or regional transmission organizations to basically to separate the transmission system from the original like utility structure there. So we have like open access platform. So everybody who can generate can access this network and deliver their electricity or service to the customers. And to the actual customer, we can have different distribution companies there. So like DTE, originally also, for example, owns transmission assets, and then around 2000, between the 2000 and 2005, I believe, if I remember the time right. So the transmission asset of DTE has been separated and form a new company called ITC now. So that's part of that, like utility deregulation or reconstruction there. So this will bring more competition to the market. So theoretically, the customer will get electricity in a more affordable way and reliable way. So on the structure of the power industry here, so we have like a federal or regulatory agencies like FERC. FERC stands for Federal Energy Regulation Commission, and SEC here, Securities and Exchange Commission, and also we have LERC. LERC is a non-profit organization. It's a North America Electricity Reliability Corporation. It basically recommend all kinds of like recommendations and rules for managing large power systems. So the utilities could have the individual owned, the federal owned, or the company owned. And R&D basically been done by universities, utilities, and also we have EPRI, Electric Power Research Institute, and companies and national labs. We have Department of Energy have various national labs, and This map shows the U.S. power grid, and we clearly can see from this, figure here. We have like a Western interconnect and an Eastern interconnect, and also Texas is a little bit special. We have Texas interconnect there. It's managed by ERCOT, Electric Reliability Council of Texas. And you probably have heard about, the extreme weather event happened in Texas in this past, February. So Texas basically is like a standalone system. It has a very kind of a weak link to this Western interconnect and Eastern interconnect. Some people said if like ERCOT could have a stronger connection with Western interconnect and Eastern interconnect, the situation could be a little bit better. But yes or no, the actual, what happened, for the electricity crisis happened in ERCOT is a little much more complicated than, just the tied power line, transmission lines there. So actually, a lot of areas, not all of the whole U.S., but many places in the U.S. are managed by RTOs and ISOs, the regional transmission organizations. Now we have the California ISO, we have Midwest ISO, and actually this Midwest has changed its name to Mid-Continent. It actually is already extended to the south as well. And we have PJM ISO or RTO here. PJM actually, in terms of the generation capacity, is the largest in North America here. And we have many others, New York and New England, and also certainly we have ERCOT here. So those are electricity market-based operation here. So so like what I showed in the previous slides here. So the electricity or the service provider will compete, provide like a bidding curves there, and a customer can, decide, which one to buy. So now let's look at some hardware. Let's see how the electricity is being generated, right? So we know the electricity can be generated from various sources there. We have different types of generators. So worldwide, the electricity being generated mainly from fossil fuels still. Although the renewables have really taken exponential growth in the past decade. From coal, natural gas, and oil. I'll show a slides about like the generation mixture in the U.S. And probably worldwide as well. And we certainly know we can generate electricity from nuclear and renewables. We can generate electricity from wind, solar, hydropower. If in the U.S. and we'll see the amount of electricity generated from hydropower and wind are pretty much at the same amount now. And we can see here for the central power plants, units is really big. So this is a GE, a gas turbine for a combined cycle. The combined cycle can be really, really efficient. As you see here, there is a 62%. And that's a really high efficiency here. And so for for some thermal like core units, steam turbine, for one single unit, the capacity can go as high, like over 1,000 megawatt there. And this figure shows a hydro generator there. It's one of the units in Three Gorges Dam. I believe that's the largest, hydro project in the world. And this one is 700 megawatt. Actually, I think the peak probably is higher than that. It may be 750. The total, they have like 32 units. So it's really big. It can generate a lot of electricity. But I know for single hydro units there, they can also go over. The largest units now can also go over like 1,000 megawatts. So it's really big for those units. And so when we generate the electricity, we need to, particularly for those centralized power plants, so we need to deliver or transmit the electricity to some other places, right? To low centers, to big cities. And so we need to transmit the electricity over long distance. To be able to do that, we need to boost the voltage up to a high voltage. So normally the electricity we generated at the generator there, the terminal there, is between like 20 to maybe 40 kilovolts. Some may get 25 kilovolts, some are 30 kilovolts there. So that's not enough for long distance transmission. So we need to increase the voltage. As you see here, we need the big transformers here. Well, there are various voltage levels depending on the needs, depending on how long we need to transmit the electricity. Depends on how many megawatt we need to transmit, right? So we can use different voltage level. So we could use 750 there. That's the highest voltage level here in North America. In China, the voltage already go over like 1,000 kilowatts, which is 1 millivolts there. But we could have some other different, levels of voltage level here, like 230 or even 120 kilowatts there. And in the big cities, when the space is really, it's a constraint, so we can use GIS. GIS here stands for the gas insulated substations. So it can really, it probably can, like for example, this whole substation here and can be put into a house. So it's very, very compact. So for example, in New York or in Chicago or Los Angeles, those big cities, they tend to use this kind of GIS there. And when we go to transmission level, the voltage level also drops. Certainly we cannot use a high voltage there, right, directly. So we need to step down the voltage to distribution level to the voltage level that we can use. So typically at our home, you can see 120 and 240 volts. So it's just like a split phase of like 120 there. So then you have those like opposite phase angle there, you got 240 there. So the actual topology also changed from like an intercollective, like a loop kind of diagram to more or less a radial feeders. Okay, like a star collection like that in the distribution there. Although with a new development, so when we have those distributed generators, as I'll touch upon that later on. So we could have like I don't know what happened to my screen here. We have distributed generators. We can have various distributed generators that can collect it to the distribution level directly. Like we could have our solar roof. We could have like maybe a 1 turbine generator in our backyard. We could have like energy storage. And we could have like EV, right? We can have like a bidirectional EV, the electric vehicles. We can do the vehicle to grid applications. So with that, we can have we call the prosumers. Can have a prosumers here. It's a producer as well as a consumer there, a prosumer. So those are all new development happening right now. Sorry for something happened to my screen here. So we are facing, growing challenges here for in our, power systems here. Globally, we're going to see ever increasing electric demand. Although in the U.S., I have to say, the electric demand is fairly stable. I have a slide after this to show that. And also the fossil fuels are non-renewable. The more we use, less is left there for our future generations here. And of course, climate change is a big challenge here. And as you can see, we have seen more and more extreme weather events. And the various level of government are facing increasing environmental regulation pressures. Like in the US here, we also set a goal there for the emission neutralization, right? So particularly for the utilities and power companies, they are under pressure to how to change to meet those climate change goal there, the emission reduction goal there. And so if we go with renewables, then another challenge we have to deal with is the intermittent output from those renewables. When solar are not as dispatchable as the regular conventional like the thermal power plant. So how to deal with it? And as we have the new type of loads, right? We have electric vehicles, and we have a lot of charging loads at home, right? We have all kinds of phones and those kind of things. And last but not least, the aging electric power infrastructure. I use aging here, probably is already aged. Okay, many critical devices here are very close to their lifetime. So this some detailed slides to show those challenges here we're facing. So this slide shows the global electricity generation here, and we can see it's increased kind of really fast worldwide. But as I said, the electricity demand here in the US is fairly stable. It may have like in average like less than 1% increase, but for the worldwide there's around 2% annual increase. So to be able to meet this kind of like increase in the demand, we need to find a ways to generate electricity, right? But for the fossil fuels, let's look at what the reserve we have here. So based on the current, the amount of reserve we know, and also the consumption rate of 2017. So the coal can last for 114 years. It's relatively, abundant, right? But that still can only last for like 114 years here. Oil, a little bit over 50 years, and for natural gas, also like just a little bit over 50 years here. And how about the nuclear? Even for the reserve of uranium, that's the most typical material used in those nuclear power plants. It's also limited. It's around like 130 years. So, and plus those are not renewable. Those all are not renewable here. So if we look at, the global, the greenhouse gas emissions here, particularly if you look at the carbon dioxide emission there, you can see this is an exponential growth curve. It's a typical exponential growth curve here, right? So we need to do something. Those kind of environmental impact has a very large time constant. It's not something we do something today and we're going to see the impact tomorrow. It may have impact the whole system in many years to come. But we already see the alarming increase like extreme weather events. And if you compare this curve here and this one, we clearly can see the same kind of pattern here, right? So the events of flooding, storm, and drought, is really on the rise. So people are, scientists, engineers are working on it, trying to say how to really curb or reduce our, emission here. if we do not do anything here, as you see, it's going to go along that kind of trend there, right? But I think good news is that like various countries already announced their goals or plans, to reduce the emission there. So based on what they have promised, hopefully, the emission going to go like this. This is based on the current policy. We could still get like a 2.8 and 3.2 Celsius degree temperature increase though. And well, the yellow one here shows some more optimistic kind of like reduction there. But I'm not sure whether we can read that past. Okay. So I got this. I would say it's a very interesting figure to show. I got this from Wikipedia. These are the list of countries who have committed, for emission neutralization. So, for example, China said that reach that goal by 2060. The U.S. goal is 2050 to reach this emission neutralization there, and particularly for the electricity generation there. The DOE or the White House and the Department of Energy has a goal there to reach 100% carbon-free electricity by 2035. So which is like 15 years earlier than the overall goal there. So it is true that the electricity right now is one of the major source for the greenhouse gas emission. So look at this figure here. This is the greenhouse gas emission profile from 1990 to 2019. So the electricity contributes about 25% of emission. If you look at the whole emission there. So the two major ones are the transportation and electricity generation. So if we really want to do something there, we need to reduce the emission for the electricity generation, due to electricity generation. And actually, we have done a lot of effort towards that goal. As you can see here in this slide here, in the past like 30 years, the U.S. generation mix profile. So you can see the amount of electricity generated from coal has been significant drop recently. And you can see a cleaner generation technique like natural gas, particularly with those combined cycle there, as definitely increased quite a bit. And another increase, of course, will be the renewables. The wind and solar has really picked up, their speed now. So I'm sorry, here what happened. Another slide to show, the generation mixture for 2020 here is most recent one, and we can see the coal now, the total amount of electricity generated from coal, even less than nuclear. And natural gas is the dominating one. It's contributing at 40% now. So like 10 years ago, like the position of coal and natural gas is just like a swap. Okay, and another thing we need to notice here is, I want to have your attention here, is the renewables. The wind now is already surpassed the hydro, and it generates more electricity there. So it's 8.4% of electricity now is generated from wind. So so that's really a significant improvement, achievement. So but when we have the more renewables here, we're facing new challenges. There are more uncertainties here. As you see here, this is like the solar generation profile for a typical a solar panel. It's a normalized PV output. So it's a lot of variation there, right? Although we can predict There's a lot of prediction algorithm we can use, but still we cannot do 100% accurate prediction there. And you can see from here, this is the actual output we measured for the solar system, on our campus. We have a solar system on the engineering technology building there on the roof. And in August 21st, 2017, there's a sun eclipse. So based on the data we collected, we can clearly see when that happens, the solar power drops there, and then when they come back, you can see a big variation there. And also, we can, when the cloud comes, we can also see that kind of thing. So it changed, it's changing there. And also, you can see this is the one speed change over the year. So how to, still deliver like a reliable and stable and with good quality of electricity to customers? That's a big challenge there if the penetration of renewables are getting higher and higher. So so that's definitely something we need to do research, and we need to come up with like a reliable and resilient system. And this slide just show the trend here, like in the past like 10 years or so, the average like number of interruptions or average duration of the total interruptions is on the rise. So we need to do something that addresses it. Particularly, we're seeing more renewable collected to the power grid. So not only the renewables, intermittent renewable sources can bring the challenges, but also the increase in EV, number of EVs on the road. So and you can see all the major auto manufacturers like General Motors, Ford Motor, Chrysler, and so on, so forth. They are basically going to turn into EV company. So sooner or later, the majority of the electric the vehicles will be electric vehicles. So that will actually put a lot of pressure on the current grid, because the current grid, not only they are aging, but also they were not designed for handling a lot of electric vehicles. So we need to do something there to handle this type of a new scenarios, a new challenges. And as I said, the electric energy infrastructure is aging and has been aging. And as you see from this slide here, for the core units from various regions here, like the average age is 40 years, and for the steam turbine, there are some of them already 50 years old. So although for some, like maybe the gas turbine combined cycle there, maybe are relatively young there, but still. So in general, and also the transmission asset, right? So, and substations, we need to do something there to keep the system, reliable, while we are having this kind of aging, infrastructure here. And also say, well, the easy solution, you may say, okay, how about we just replace them with new? That would be very, very expensive to do it. So how to come up also a cost-effective way to do it, right? And so that the customer can have affordable, electricity. That's also a big challenge. So there are people are proposing all kinds of solutions. Here I just list some of them. By no means this is like a complete list. It's just like the solutions I just summarize here is so for example, the first thing is to address the electricity generation. We need to go with sustainable energy development. So although there's a big challenge there for the wind and solar, we still need to go that way to produce electricity from renewable sources. And we're going to take a hybrid approach. So we have this centralized backbone, as you see there, those high volume transmission lines with the big power plants, with the big generation units. And also we have now we have a lot of distributed generation systems. For example, we can have, like a solar panel on like commercial buildings, on residential homes, and we could have like energy storage for the communities. We can have like a smart buildings, do all those kind of things there. And microgrids is an interesting development. So microgrid is a good platform which integrates, various distributed, sources here and just managed by their own. And energy storage definitely is probably right now is like a most promising solution to address like an intermittent generation challenge brought by wind and solar. So, but for energy storage, we can have the larger one, we can have the centralized one, we can have the distributed one there, we can have stationary one, or we even have like a transportable one. We can put some like energy storage on some like a transportable platform. I'll talk about this later on. So, and also demand response. So in addition to like do all kinds of control from the generation side, we can also do the control at the customer side. So this kind of like add another degree of control there. So certainly, hopefully, the system can be managed better and more efficient and more reliable. And there are various technologies, for us to achieve to realize those solutions. So we need advanced computing and communication and control methods. We need fast optimization algorithms for large and complex systems. Power system is so far still the largest like a man-made like network, and maybe internet is another one there. And also we need like a AI and machine learning based method and also power electronic converters to convert electricity from one type to another type to meet all kinds of needs there. So now let's see first, like look at the sustainable energy development, and this is what the renewable generation in the U.S. and we can see here the renewables, the green one. In like 10 years ago, it's maybe just a little bit like less than 5%, and now it's almost like over 20% now, and it's going to increase to 42%. When we really reach that goal there, right? So for this one here, apparently it's not exactly like the carbon neutral there, but we'll see how to really get rid of all the carbon emissions there by like go there like 2035. And if we just look at the renewable there and solar and wind are the two major ones. And solar, although now it's still much smaller compared with wind, but it's going to pick up according to the prediction of the Department of Energy here. So then comes the question there, and we can see there the coal units have been phased out by and been replaced by like more efficient and cleaner generation units. But this slide shows some interesting another criteria to look at whether this is a good unit. So we compare the two parameters here. The levelized cost of electricity, LCOE, and also levelized avoided cost of electricity. So if we have a technology of generation, which is on this region, on those all exactly on this diagonal line here, then that's a very, I would say, competitive or a promising technology to go with. But on the other hand, if it is on in the right bottom here, then that means it's not so good. It's not so competitive because it can be replaced by others, as with less cost. So you can see from here, from the wind and PV and the combined cycle here, those are really competitive. Not only it is cleaner, it's more environmentally friendly, but also it's also more economically competitive. So it's that's why those units are being built more, and core units particularly have been phased out. So in addition to those centralized, large power plants, although even for those centralized power plants, we can generate, electricity from various sources there. We have a distributed generation sources to have a hybrid system. So we could have like a backbone system here, and with all kinds of like DGs. And those DGs could be managed by those microgrids. Right, so people are now have like a super grid or mega grid with interconnected large power plant, and also with microgrids and nanogrids, so attached to it. So that's got a system level of like a hybrid structure there. And even for a specific like a system there, we could have different sources. We could, for example, we could have like a wind and solar hybrid system, like the one we have on our campus. We have a wind turbine and a solar panel there, together with some energy storage, like a battery. So here, just list some typical generation sources here: coal, natural gas, nuclear, hydropower, and those renewables like the biomass, concentrating solar power, photovoltaics, PV, and so on and so forth. Even for this one is like a micro turbines, so we don't have to build a huge dam there for generating electricity. And we have storage. We can have the pump hydro. That's still the largest kind of thing we have. And we can have battery. We can have like a magnetic small scale superconducting magnetic storage system, and so on and so forth. This slide shows the hybrid energy system that have been deployed in the US, and we can see in the various locations there, and you can see some of them are already pretty big, like over 150 megawatt. And well, this is the data, in 2019. That's the latest I can get. But based on that, we can see here in Michigan, we haven't seen any like a big system here, and I believe we should work on that to get some, a good, hybrid energy system there built in Michigan. And for energy storage, so that's for the previous couple of slides we talked about the sustainable energy development from various sources, and we also need energy storage to particularly handle the varying output from renewable sources here. So there are a lot of energy storage techniques we can use to store electricity there, but to store electricity at a mass level, it is still a big challenge. As I said, the pump hydro is still the most feasible way right now, and also still the most cost-effective way. But the battery technology is picking up because the electric vehicle, the auto industry, they really reduced the cost of battery. So now using like a stationary or the battery storage system for power system application is become more and more affordable and attractive there. So, and in addition to pump hydro and batteries, we have like a fuel cell and electrolyzer. We use a fuel cell and electrolyzer and generation and storage, and of course the energy is stored as a hydrogen. there, and flywheel, capacitors, and the superconducting magnetic, energy storage systems in S. So as I mentioned before, so energy storage can do a lot of things. They can be used to accommodate renewables, right? If there's more renewables, we can charge the energy storage we have. If there's less, we can discharge the energy storage, right? It can be used for those ancillary service for the frequency and voltage regulation, and also can provide reserve. So we know for the power system operation there, we have to provide certain reserve in case something happens, right? And there can be like larger scale, utility scale energy storage. We could have like a community-based energy storage, or we could have some distributed storage just at the building or home level. So and this is pretty interesting, and people have been doing research on the transportable as well. The transportable energy storage, for example, we could do something like aggregating, electric vehicle virtually. So through like something like we call the virtual power plants here, of course, will be like a virtual energy storage plant or energy storage station. So aggregate those individual EVs and to have them, charge or discharge in a coordinated way. And we could physically have a transportable energy storage. Like for example, here we could put energy storage on 18-wheel on the truck. And we can put those energy storage at some critical locations, strategically put at those locations. So take the Texas, for example. What happened in the February? If we could have this kind of like energy storage, transportable energy storage here. So if we have that within the state, so those like mobile energy storage can move to some critical locations there, or the nearby states like Louisiana, Arizona, or maybe other states there. When we have those mobile energy storage system, they can drive down to support a particular region there. So if say extreme weather condition there, or even for some other event, this will definitely improve the power grid, power delivery, resilience, and reliability. So another thing, people have been looking at is, as one of the solutions to address the ground challenge there is to go through the demand response. The demand response, well, right now we probably really do not do this. Most of us, we just go home, turn on whatever the appliance we want to use, and we really do not do much of management there. But say the demand response here is, say, the customers can change their behaviors, the consumption pattern in response to the changes of some incentives or some signals from the system operators, so that the whole system reliability can be improved, particularly when the system is in need. And certainly we can do this without actually compromise the customers like a comfort level. So there are quite some like appliances in our home, for example. We really do not care when they're going to be turned on and off, right? And for example, if you have an electric vehicle, probably you say it probably does not matter. Say I'm going to charge this vehicle right now, or I'm going to charge it like a couple hours later. If you have that freedom to do it, then well, to you probably does not change anything. And for example, the de-icing cycle in your refrigerator, or when you're going to do your laundry, like a dryer. So those things probably you can do it at a time that is as good for the system, but also does not affect your daily life there. So that can really, produce a lot of benefit thing. Like we can really, reduce the peak demand, and change the load profile, make the load more stable, right? And that can reduce the loss as well. And for some certain program, we can do the load shading there. We can cut that, because then we can take the system from a very stressful or dangerous situation there. So to be able to really achieve those goals there, right? There are a lot of things we need to do. At least some enabling technologies here. So we need to have advanced power electronics. For those wind and solar, we need power converters. We need to develop new control methods for this large and complex law-needed system, right? And we need advanced communication and sensing, technology there. We need advanced data, and information processing. We need big data, kind of analytic methods there, and we need machine learning, AI, kind of advanced computing there. Like very soon we'll have a talk on that, like edge computing, and that all can do has a good, I believe will have a good application in power system here to address the big energy and environmental challenges. So with that, I want to switch gear a little bit to talk about what have been done specifically, in my team at the Wednesday here. And so what is our efforts and approach to? So I will talk, in like three big categories here in general, like power systems here, and also the energy storage and the power electronic converters. So the first, the area here we have been working on is, we have been doing modeling, control, and management of hybrid energy systems. We're looking at modeling of various, distributed generation sources here, like solar, wind, microturbine, fuel cells, and their control and their optimization, and how to do the sizing, how to integrate them together, with the existing grid, and so on and so forth. And we also work on smart grid technologies here. We work on an advanced analysis method, and we'll talk about some examples there for cascading failure evaluation and mitigation, for voltage stability analysis. Voltage stability is still a critical problem for large, interconnected power system there. And also for a power flow tracing. That is useful for tracing emission flows, because we generate electricity at various generators. We deliver electricity. Of course, electricity, just the electrons flows. There's no emissions there. But when we use it, actually we should also be part of that emission responsibility. So we develop a method how to kind of quantify those emission flow there, and also for the asset management, because the devices, equipment are getting old. So how to come up with the optimal asset management, right? How to do the maintenance, how to replace or retire those devices there, and so on and so forth. And also for demand response. Say we could come up with a more effective or environmentally sensitive or guided energy usage. Okay, and also this power flow tracing I talked about there. So for example, here we really a couple of years ago we worked on this a hybrid solar, wind, and the fuel cell system there, and we talk about how to model it, how to implement it, and we actually, in addition to those theoretical analysis, we did build one on campus Okay, and I have I have some picture here. So this is like a hybrid system we built on the roof of engineering technology building here. So so that's a like a wind and solar, and we also have the battery storage there. So that's the work we have done on those like a hybrid energy system and microgrids as well. The microgrid is, as I said before, is a great platform for integrating various distributed generation sources. And based on this kind of concept, people have been proposing, like, for example, nanogrids, and which we can dealing with individual homes or buildings. And recently, we work together with Lex Energy and the University of Michigan. We submit a proposal to DOE on this kind of smart building kind of thing, to really control the building energy usage profile to provide service to the utility, to the power system. So it's like a stack servicing. So first of all, we can do maybe follow those regulation signals, or we can do those kind of arbitrage, like for the energy market there. But at the same time, we need to follow. We need to guarantee the users, to keep their needs. We don't want to have like a unsatisfactory customers, right? So all this, I believe, a lot of methods can be used. For example, like machine learning methods can be used to come up with a good management strategy, how to provide incentives to customers, right? All those can be developed. And based on that, if we can manage the individual homes good, then we can come to the level to manage, a distribution level at the community level. Then we can further go up to like a higher level. So in this way, the whole system can be managed in a hierarchical way here. So I already showed this slide to you. So part of the result of the work we have done on this hybrid energy storage system there, summarized, in the 2 books here. Like one is modeling control of fuel cells for distributed generation applications. Another is like the photovoltaic distributed generation system there for both grid collected and standalone system there. So this is just another example. It's more target for the large interconnected power system there. And we know the cascading failure or blackout, although it's rare to happen, but it can cause big impact. So it's a really important topic to study, saying how to evaluate the risk here. And if we have that kind of risk, which actually the risk is always there, how to mitigate or how to reduce that risk. So we, one of the PhD students in the team, Wasim, is working on this, and we are taking, working together with Professor Feng Ling. We work, take a discrete event system, DS approach, to develop this kind of online limited look ahead policy, ALP approach, to evaluate the potential risk and also to mitigate, the cascading failure here. So we did some simulation study for the IEEE 30 bus system here, and we can see our method is actually better than a typical the emergency control method that we use currently. And this is just another the work we have done. I'm sorry for not being able to really touch go deep on a specific topic here, but if you are interested, we certainly after this I'll be more than happy to talk to you on any like a specific topic I just mentioned here. So this is just another example of work. You know, it's a transfer impedance-based system equivalent modeling. So for this model, we actually build an equivalent circuit from a specific load to various generation sources. So in that case, I know, for example, I can figure out, say, at a specific time and specific location where the electricity is actually coming from. Of course, you may say, okay, if it's just an electron flow there, how come you can really get, the contribution of your electricity usage from those various generation sources? So this is, this is a big, it's a big puzzle, and we use this like equivalent circuit based method to come out with that kind of solution here. We did it for like absolute amount, and also for the marginal, like allocation there from a specific location of low consumption to various generation sources. That one, another PhD student, Ting Li, has been working on it, and that is more or less on like a financial kind of allocation there, but based on like electricity market there. But for this one, this TSIM is transfer impedance based. It's based on the electric circuit, purely based on the electric circuit here. And we get this kind of equivalent circuit, so we can reverse back tracing the electricity to the various generation sources. So the application of this technique is, it can be used for the voltage stability analysis. It can help identify the most vulnerable bus for this kind of issue. So in that case, then we can say, we identify that bus, we can do something about it. And we can also identify which generator is going to affect most to that location there. And we can also do something there. And not only for this stability analysis, we have done the simulation there for a real kind of system like this polished, test bench here. It's like over 2,000 buses, almost 3,000 buses here. We did the simulation, we verified our method, but also this TSM method, this power flow tracing method can be used for the emission quantification here. So we can, for example, at any location here and any time, we can tell you at this moment for 1 kilowatt hour usage now, what is actual your various sources. You can link that to the various generation sources here, and then we'll tell you what is the emission factor for that. Because if we look at the overall emission factor there, the average one there, it does not really give you the detailed picture there. So with this one here, we can give you the detailed information there. And well, this slide clearly shows that. So here, like we have the, I don't know how many here, maybe 14, maybe 18 here, like a different the field type and the prime mover type. We certainly with different efficiency, different efficient factor here. So if you just use average, then certainly you're not get the accurate picture there. So if you look at the average, look at the call, the emission of like a carbon emission here is like a 2.2 pounds per kilowatt hour. For natural gas, less than half. For oil, for petroleum, it's almost the same as the coal there in terms of carbon dioxide emission there. But so if we do the average here, we certainly going to lose the detail here. And also, even for coal, there are different types of coals, right? And so, well, with that, we can see this one, see all the details here. So that's why we need to identify, and also for the renewables, there's no emission, right? Nuclear, this kind of carbon emissions. We need a technique which can tell, okay, at this location here, what is the emission here, right? So we have to trace the power flow back to the generation sources here. So, oh, sorry. I don't know what happened here. Okay. Work with Dr. Miller and many other colleagues here. Particularly Dr. Miller's team. Dr. Miller actually developed a company for this E2I, I believe, it's Energy Emission Intelligence, to help you actually identify the emission at any given time and given location there. Okay, I believe we started in MISO and now probably is extended to PJM and maybe California ISO as well there. So for that, we can do this demand response. We can develop like a environmentally sensitive or guided demand response. We can tell you what is the emission signal there, and people can respond to that, say whether they're going to respond it or not. So I can tell you right now, the electricity is clean or electricity is kind of a little bit dirty. You want to do it now, or you may want to postpone a little bit to the future time. So, and that, certainly they can do this by doing this kind of demand response. And we have also worked on like a reliability evaluation and optimal asset management. I've been in contact with like DTE. Hopefully, someday we're going to work together on this. So we can do like a probabilistic analysis for the sparing and find the right time, the right equipment to retire, and also come up with a effective and optimal maintenance strategy. And we also do this online monitoring and fault diagnosis. That's the work I've done, many years ago, but I still keep that, in my research portfolio. So here we have, particularly for this kind of like reliability assessment and evaluation and asset management, it's a data-driven approach. We have a lot of data. We have the historical data there from all kinds of tests and records. We can look at all the system reliability indices here, we could have like online monitoring, data which can be fed in real time. So with that, we can have come up with some analysis or decision making algorithm. It could be machine learning based to tell us to come up with a optimal strategy for maintenance, for doing all those kind of like a sparing and retirement kind of decision there. So, and as I said, we also work on the online monitoring of the critical device there in the power system, and also for diagnosis. We develop a power transformer for diagnosis system. It's like an expert system there. You put the data there, and you put whatever information you may have. Then the system will tell you what kind of problem might be, or if there's any problem, or everything's okay, or if there's anything wrong there, the system will tell you, okay, what the further action you might need to do. For example, you probably want to do some dissolved gas analysis, take some oil sample there. You may want to do some partial discharge tests, all those kind of things. So so this kind of system can actually be extended to others, like devices. It can be extended to generators, to the potential transformer, current transformer, and other like substation devices as well. And we also work on the energy storage devices, and work with many colleagues here at Winstead and other institutions, like here at Winstead, Professor Wang, and we work on the battery characterization methods, how to jointly estimate the battery state of charge as well as the battery parameters, and then based on that we propose like the SOC based uniform like a battery management system for either a utility scale or large scale battery storage system there, as well as like the battery packs inside the vehicle. So the not only for those physical part we're going to build those. I have a picture to show a like the hierarchical like a multi-level converter for those type of energy storage system there. We also do at the system level to how to like to find the optimal place in a large power system for those battery storage system. So for example, this result is done by one of the PhD students in the team. He already graduated, Zhongyang Zhao. Work on to find in PGM as a specific system here to find where if we use the battery to provide both the energy service as well as auxiliary service here for the regulation here. So regulation, we could do the regulation A, which is a relatively slower, or we can follow the regulation D signal, which is faster there. Every like 0.2 seconds, there's a signal there sent by the RT or RSO there. So if we want to provide our service, so we come up with algorithms here. Okay, if we want to provide that service, based on the system load in the past, history, the record there, and consider the variation, consider the uncertainties there. So where will be the best spot to put those energy storage devices? So we could do it from the perspective of the actual like owner of the energy storage device, or we could do it from the perspective of the actual system operators. So from this two perspectives, the result could be different, because if we from the angle of the system operator, we could have maybe the all information of the system. But if we from the market participant, so if I'm the owner, if I'm the investor, I want to invest this energy storage system. I want to earn money, right? I want to have the revenue there. So, but I do not have the whole information of the system. I only have the information that is open to the public. So where to find the right, place to put those energy storage is quite a different story. So not only the objectives are different, but also the information availability is also different. So those are the work we also have done there. I'm sorry. And I want to show you a short video which we built. We built a solar assisted, a battery management system. We actually put it on a golf cart. This is what I want to show you. The next slide. I have a small video here. Hopefully you can see the video and hear the music. So this system, we said we're going to use energy from the solar to help balance the battery in an electric vehicle, and so the battery lifetime can be extended. It's been better managed, to keep that kind of uniform SOC, operation there. Well, if the battery is already, balanced, then the extra solar energy can be used, just to maybe provide some additional mile range there, to charge the whole, battery pack. So that can maybe add, 10 to 20 miles there. Okay. So that's, for the work on the power system side, and I want to talk about energy storage, topics there. I want also to talk about the power electronic converters. I may want to spend like 5 minutes or so to talk about this, and after that I can open to the question there. But certainly, if you have questions, feel free to ask. For power converters are actually the core and enabling technologies for not only the hybrid energy system there we talk about, like solar one and so on and so forth, fuel cells there, right? But also particularly for electric vehicles, right? Electric vehicles, we need to, as you see here from this figure here, there are all kinds of power electronic converters here. We have DC to AC. We convert the energy from the battery and to drive a motor to propel the vehicles. And if we charge the vehicles, we convert that the electricity from grid AC to DC. And maybe we have a lot of DC to DC in the middle as well. DC to DC particularly is needed for fuel cell applications. And also inside the vehicle, right? We have the high battery, high battery, body here. Right now it's 400 volts, and in the future could be 800 volts and even higher. And we also have 12 volts. Those are low voltage for like electronic loads, for entertainment, for control. Particularly in the future, if we have like autonomous vehicles, so the computing, going to consume quite a significant power there. So we need to provide them like the low voltage. So we need to have a good DC to DC to provide to convert the voltage, from like a 400 volts to like 12 volts or even lower. So this is a big challenge, because the ratio here is so big. So we are now, for example, we are now in contact with Eaton and other industry partners to for a project on this, to develop this kind of high ratio, converters, and also, for those renewables here. Okay, so we have to work on the various converters, AC to DC, DC to DC, and DC to AC, for the different applications in electric vehicles, in power system there, for example, for FACTS, the flexible AC transmission systems. Basic FACTS is a power electronic based devices to control the power flows and also sometimes provide the reactive power compensation to the power systems. We work on both like silicon-based devices, which is a traditional one, as well as the new device, wide bandgap devices like the silicon carbide and gallium nitride, based, converters. And recently, we are also looking at the semiconductor device packaging. Professor Yong Xu and I, we are in a discussion to come up with some, packaging for the new silicon carbide devices. So it's all for the goal of, to achieve like a cost reduction, cost effective, high efficiency, high power density, and also high reliable, converters. Those are particularly important for electrical vehicle application because we have like a limited space to put a converter in, right? This is the example of converters we work on. It's called Detroit rectifier. This is the lamp we give that. We also have a patent. It's currently pending on this. So this Detroit rectifier it's a 4-level converter compared with the typical like 2-level there. Although the level components are more compared with the 2-level there, but you can see this 4-level there is smoother. If the AC side is more or less like a sinusoidal compared with the 2-level here, right? So this is better come with a sinusoidal one there. And you know, we can use for the same voltage level, because it's a 4-level, we can use a lower voltage components, which can much reduce the EMI and also reduce the switching loss. Okay, and that can help us achieve higher power density, higher efficiency, and can you know, certainly, you know, because the efficiency is improved, so the amount of loss, heat loss there is also less, so we can go either with liquid or air cooling. So this technology, like a Detroit rectifier, can be used for a lot of applications. Can be used not only for like an onboard charger. This OBC means onboard charger here, as well. They can be used for offboard charger, for the charging station, for the fast charging stations there, for the wind energy system, for uninterruptible power system, UPS, and so many other applications here. Whenever there is a need for converting AC into DC, particularly for high power and high, you know, current applications there, high voltage applications there. So this Detroit rectifier can be used for that. And then we also work on like the new device, wide band gap device there. So we work on this 20 kilowatt GaN inverter. We work on those silicon carbide based inverters there. This is just some example here. And currently we're working on this 180 kilowatt DC-DC converter for fuel cell vehicles applications. So it is, you know, it's really high. It's very challenging to build. Of course, a lot of things we have to consider. For example, if even say we said we're going to achieve like a 98% of efficiency. Even for that, say the 2% of loss here is about, you know, like a 4 kilowatt loss that we have to take it out was the cooling system here. So so we have to, a little bit detail about this 180 kilowatt converter here. So we go with like a modular design and interleave them together. So particularly we say this for fuel cell vehicle application that we want to reduce the ripple taken from the fuel cell. So with this interleave, like a modular design, we can really reduce the ripple. So it's like show an example of interleaving. And the couple inductor, we also use the couple inductor techniques there, so we can further reduce the ripple and to help balance the low current for each of the facet or each of the module. You know, compared with the regular one without a couple inductor, you know, certainly the ripple not only be reduced overall, but also for each phase is being reduced. You can see from here, compared with this one here. Although the overall may be the same, but each phase can be reduced and also can help reduce the loss of that inductor. And this is like an overall waveform of that A-phase, you know, interleaved converter there. You can see each phase here. We see like a 25% kind of like a ripple there when doing the ready application there. But for the overall current, if you look at here, it's almost nothing. The ripple has been significantly reduced based on the interleave like techniques we use, as well as the couple inductor, you know, techniques here. So that is definitely good for that, you know, the fuel cell application there. And also we use the soft switching techniques. So so the regular one there, there's an overlap between the when we do on and off of those switch device there will be a overlap region. That is a loss. And every cycle, switching cycle, will have that. So for example, the switch will be switched very fast, from kilohertz to tens of kilohertz to like 100 or even megahertz. For example, the one we're in talk with the industry for that very high volume ratio there, that's going to be, we're looking at the switching frequency of like maybe 1 megahertz. So we have to reduce the area here. So that's what we did here. As you see here, this is the real measurement curve. We achieved the soft switching there. So soft switching there, there's no, the switching loss has been much reduced. So this is another example. The converter we developed for the utility scale, like energy storage system there. This could be used for like for managing the battery pack in the electric vehicle there as well. And I believe, that's it. That's all for, my presentation today. And thank you all very much. If you want to interested in any specific topic here, because particularly from the work we have done in the team, I just give a brief introduction there on various work projects we have worked on. But if you are interested in specific one, let me know. We can talk after this. And if you want to know more information, you can go to my website. And also we have a YouTube channel there. We just put some video there. We'll start to promote it, but you are welcome to go there and take a look. All right, thank you all very much. I'll be happy to discuss with you, or if you have any comments or questions.
Thank you, Caisheng. So we still have some time here. If you want to ask any questions, please just unmute yourself. Go ahead and ask.
Yeah, I believe I was advised to give like 30 minutes for Q&A, right?
Yeah. We planned, a lot of time here for the question and answers here, in case that.
Hi, Wei-san, can I ask a question?
Sure.
Hi, this is Azad. Hi, Caisheng, nice presentation. Thank you. So,
hey, Azad, how are you?
Hi, thank you very much. So one question I have is about the biofuels and their contribution to this green energy, because it seems, at least in the US, many of these bio generators are popping up, or at least they are in production in the US. So how does this come into play in this this picture actually? So what is your expectation in terms of like improving the stability, or basically the intermittency of the solar and wind using the biofuel?
Biofuels or biomass or other thing like, from the biomaterials. I think, currently the contribution from them is, first of all, it is a renewable source. It's a renewable source for generating electricity here. But as probably I showed you in the previous slides here, if I can go back, there's a generation mixture I show you. I don't know where I put it there. So you can see here, the biomass is relatively small at the moment, right? So, but it is renewable. It is dispatchable. So which means it can be controlled, like regular, like thermal power plants, like coal. That's definitely is a good thing compared with like other renewables like wind and solar. So wind and solar, in general, they are intermittent. They're not as dispatchable as other renewable sources here, like hydro, and we use like a bio here. but with the energy storage, with the prediction there, that situation, to answer maybe probably the second part of your question there, how to address this kind of like intermittence of from those renewable sources here. So we can do like a better prediction. So the prediction algorithm is also plays a critical role here. So we may not still be able to predict exact, say, okay, next day, like at 8 o'clock, what exact the wind speed might be, right? Or what's the solar radiation might be. But in the hour range, right? We can have a very pretty accurate prediction. So with the good prediction, more accurate prediction, together with energy storage and other dispatchable energy devices, which can be turned on and off very fast. So we can handle that intermittent, those variations there. So for example, we got some gas turbine units can be turned on and off very fast. I'm not sure the biomass now can do that. Can be like as like a peaker there we call it. So we can turn on and off very fast. Probably not. But biomass, it can be like it is controllable, it's dispatchable, and with a better way. I mean, the more we'll have to look at whether it can make economic sense. If the biomass, if we look at that curve there, right? I'm not sure what I should. I forgot where it is. This curve. If the biomass can continually grow into this region, then I'm sure it'll grow. Otherwise, it's hard to say at the moment. It may stay there as a meaningful, like a contributor to that renewable portfolio there, but I'm not sure how significant that might be.
Okay, thank you.
So, yeah.
Okay, any other question from the audience?
Would it be okay if I asked a question?
Sure, go ahead.
Okay, so I've heard one of the biggest problems with like renewable energy is that, well, like from the transition of the energy source to where the energy needs to be used is like there's a lot of loss of energy. So like, yeah, like you lose a lot of energy in that transmission. So is there like currently or is a way of preventing this loss like being made and stuff? I don't know if I made myself clear, sorry.
All right, okay, thank you for the question. I think that's an interesting question here. So if I understand your question right, you said, okay, your question here is regarding the power loss here, right? And it says quite some like portion of electricity may be lost during the way of like transmission there. That is actually true, not only for the renewables, but also for other type of generation techniques here. Well, let me just look at this one here. So if we generate from a power plant, and we're going to go through the transmission lines, right, and go through the substations there, and then through some distribution transformer to step down so people can use it. So there's a whole process here. Even we say if we do not consider the conversion efficiency of the generator itself, so if we consider we already have the electricity, right? So just the the efficiency of this transmission and delivery, although it has been improved, but still it depends on where you are. The loss can be from like 5% to 10%. But typically, you may get something around 7% there, power loss there. So that's say you already have electricity, but in order to deliver this electricity to certain place, to certain location there, that's just lost it because the transmission lines are made of those conductors, right? The conductors now are not superconducting materials yet. There's a R. So when there's an R, there's a loss. So I squared times R, that's a loss there. So how to reduce this? The two ways to do it. People have been working on it. One is certainly for the same amount of power, we increase our voltage. We increase our voltage to really go to like a very high voltage. Right now here we have like a 750, right, or 765 kilovolts. Okay, please bear with me. My very bad handwriting on my screen now. And also, so when we, for the same amount of power, if we increase the voltage, then the amount of current will be reduced. So if you reduce the current by half, the loss will reduce by 4 times. Okay, and this is one way to do it. So we're going to go with a higher transmission system there. Another way to do it is go with a distributed. Go with distributed generation sources there. So this one not only going to increase the reliability, because for large centralized power system there, we have like a single failure, point failure kind of risk. But if we have a distributed generator, those things can be installed just very close to the end users. So for example, I can have a solar panel exactly on my roof. So I do not have to let the electricity transmit over a long distance to reach my house, right? So for that, they can, reduce the power loss. Okay, so basically, the power system now, it is developing in that two directions. So on one aspect, the system volume is getting higher and higher, and for single unit, it's getting bigger and bigger. But on the other hand, the system also get more diverse and dispersed with those distributed generation sources for more reliable and more efficient electricity development and delivery. I hope I answered your question here.
Yes, thank you.
All right, we have time. Probably we can still take a couple of questions. So if you want to ask, let me see. There's a chat room. Oh, that's just said. Nice presentation.
And I want to follow up on that renewable thing there. So sometime, when we have a very strong wind, but the system, like the load demand is not there. So we have the wind blows there, but say during the like around the midnight, the system level, the load level is low. In that case, we may have to, we call the, it may be a waste of energy there, because the energy certainly can actually produce more, but it's being capped, actually be reduced to meet the system, load demand, because we have to keep the balance between the generation and load. So in that case, yes, it's kind of wasted if we do not have a good way to handle it, because we just do, for example, we can do the pitch control to really reduce the amount of the one generation there, although it can potentially generate more. So in that case, energy storage will be useful, right? Or demand response. So we're going to follow the actual generation, the potential there of those renewables. If we have more, renewables there, we could we could charge those energy storage. And when, it's a quiet day, not much of renewable, then we can discharge those renewables. That's energy storage is about, right? So, but certainly right now, the scale, the capacity of energy storage is not there yet. It's not really at the level of like the one generation capacity. For example, one now generating about over 8% of electricity. So the energy storage capacity is not there yet. So sometime, so those generation may be curtailed to be reduced there, but certainly with the technology there, with the more this kind of energy storage devices, with the demand response there, that will be reduced. So for that part of West, I believe it will be reduced.
Caisheng, can I ask one question?
Hey, Masood, how are you?
Yes, thank you. Very good presentation. Do we have time, Wei-san?
Yes, go ahead.
5 minutes. Thank you. Very nice presentation. I have a question about the slide that you compared the technologies in terms of the economic liberalized economic costs. So here you mentioned,
this one, right?
Yes, you mentioned that like coal and nuclear are not competitive compared to PV. But my understanding is that because coal and nuclear, they are taking advantage of economy of a scale, they are cheaper. I mean, if you look at the market, when they are competing in the market, they have always the lowest marginal cost. And on the other hand, like wind and PV, they have very high capital costs. So
yeah,
can you explain that?
I think what you said is the current market. If you just look at the cost of electricity, if we just look at the cost of electricity, yes, but if we look at the levelized cost of electricity, particularly in the future, we need to consider the emission cost, right? So this is the latest. I got this figure from the latest annual energy outlook from the EIA, from the Energy Information Agency or administration.
So they are penalizing the emission, right?
Yeah. So,
but what if we use carbon capture sequestration for coal? I mean, the other technologies can be used for coal. Then the coal becomes clean.
Yeah. So I'm not sure what will be the cost if we build like a carbon capture facility there. So so we're gonna store, or we're gonna use some like find a specific like geographic like location there, like a cave, right? Or maybe underground something that we can pump, the CO2 there. But I don't know what's the cost. So this, the first time when I saw this, I'm also a little bit surprised. So when I see the cost of coal, of nuclear, is kind of, so that's why you see, the one reason here. So this one we'll have to look at not only just the fuel cost, but also the maintenance and the emission and all those things. And that's why if you look at the this trend, the coal units have been really significant drop. So if it is still really economically attractive, they will not be phased out. So that's why they put another factor there. So they put another factor called the levelized avoided cost. So which means say, if this one can be replaced with a relatively like a cheaper there, but if we want to build a new one at a higher cost, I mean, here what you're looking at here is right now, if we want to build a new coal plant, if you want to build a new power plant, so what you can get. So compare, you're going to build from other techniques here from wind or solar or maybe combined cycle gas turbine, then it's probably better to build new power plants of those rather than coal units and nuclear. So if those units are reaching their lifetime, they'll be phased out. So this is my understanding. So that's why you can also see from the previous figure here, that's why it can be, the coal units have been really been reduced, and the natural gas units have been increased as well. So Masood, I believe that your question is really interesting there, but I believe, if we go to the corresponding website of that website of this EIA here, I believe we can get more information. So what was put in there is, so the Department of Energy believes if a technology is on this diagonal line or on this region, it's more competitive other than on this side. So this side is not good. This side is good.
I see. Thank you, Caisheng. That was great.
Okay, thank you, Masood.
All right, so the time is perfect. Although I'm sure there's a lot of questions here that we want to ask. And even I have some questions, but I will ask you when we run into each other in the neighborhood. Okay,
Sure.
Sure. Thank you very much. Caisheng, this is a wonderful talk, and also thanks to all the audience that you guys. Some of you probably left, due to other meetings, but I think that thank you all for your attention. Next week, there is next Friday, because it's Independence Day, long weekend. We don't have a presentation, but after that, we will have Professor Azad Ghaffari from Mechanical Engineering talking about structured and scalable safety control of autonomous ground and aerial vehicles. A very hot topic. And I hope that some of you can join this talk on July 9th. All right, see you 2 weeks later. Yep, bye-bye.
Okay, thank you all. Bye-bye.